Okay, so this is 3, 19, 15. At its root, potential energy is just energy you're saving for later. It's stored energy. And you can store energy in a bunch of different forms. It can be relative based on the position of an object. It can be relative based on some characteristic of the material or the object itself. But it is stored somehow. We are going to explicitly not talk about chemical energy here. At its core, if we think about it in the simplest terms, that's the same thing. It's energy that's present because of the bonds between atoms. And so it's really energy of position, but the position is one atom relative to another. We're not going to do it at that level. We're doing this at the macro level because this is physics, not chemistry. So the two kinds of potential energy that we're going to talk about, you can probably guess from those two pictures. Okay, I invited that. So this is gravitational potential energy, and this represents elastic potential energy. So, okay, I had that coming. Also known as our friend PEG, P-E-G, and it's all about how far away you are from the gravitational source. In the problems that we typically do, guess what the gravitational source is? Earth. You're standing on it. Or sitting on it. Yeah, it's the Earth. We could do other gravitational sources, but we don't. That gets too complicated. And the formula is really easy. Mass times acceleration towards the gravitational source times the height above that source. So mass of the object times free fall, g, times how far up in the air the thing is. And just like all other forms of energy, it's given in joules. And we could do the dimensional analysis for joules, but we probably won't right at the moment. A couple things to note. There is some zero height, and you make it up. Remember how we say sign is arbitrary sometimes? In the case of gravitational potential energy, your 0 point is arbitrary, in essence. That's what we're going to explore. So, if I have two buildings side by side with their roofs, and here's the ground. I'll draw the ground in a different color so that we can see that it's ground. Okay, there are our buildings. If I'm standing here and I jump off this building and I'm going to land on the other roof, do I call this my 0? Do I call this my 0? If I dig a pit in the ground next to one of the buildings, does the bottom of the pit become my 0? So your 0 is arbitrary. It's basically how far you can fall. Typically, we do use the Earth's surface as 0. If there's a pit, of course, the bottom of the pit is usually 0. So, if you look at any object on your desk, your book, your calculator, your pencil, how much, if it's not moving right now, if we call the top of your desk 0, does it have any potential energy? No. It's, it's on the surface. If we think about it as being the floor, it's got some potential energy. If we have a pit that we're hanging over for some reason because it's physics and we do things like that, it's got more potential energy because it's got farther that it could fall. So when we say 0 is arbitrary, it just means really what we're looking at for that height is how far you can fall. And we most traditionally do use the actual surface of the Earth for our 0. Okay, if we have this rock sitting on the top of a 7.26 meter high cliff, and the rock has a mass of 10 kilograms, how much potential energy does the rock have? So, PEG, our old friend PEG, equals MGH. MIG. Okay, so it couldn't really be a simpler formula. Let's plug in the numbers. Okay, so we've got a number for potential energy of negative 712.206 joules. A word about sign here. We hate words about sign. What's that number actually supposed to be? Negative. So that gives you a positive. So you've got positive energy. You can just use magnitude.
Let's just forget all about sign. Let's use the absolute value of everything.
Let's not. Sig figs, we get what, 3? So this is 712 joules of potential energy that this thing has.
Can you ever add negative?
Negative energy, not for potential energy. No. No. So in saying that, right.
Forget about the sun.
So, having done potential energy, now let's talk about the other form of or potential gravitational. Let's talk about PEE, or our friend P. P.
This is all note card.
Yeah, this is all note card worthy, yeah.
Oh,
So, elastic potential energy is energy that's stored because of the kind of material you have. So, it is stored because of some characteristic of the material. The material has some amount of elasticity. And it's dependent on the deformation. That's a word we're going to use a lot. The deformation of the material. How much you can deform that material and have it return to its original shape. And deformation can be either stretching or compressing. So when we talk about springs, there are springs that are compression springs, and there are springs that are extension springs. And you've all, well, we'll look at a few examples of that. The equation for elastic potential energy is 1/2 kx squared. 1/2 kx squared. Well, you can probably figure out what x is, right? What is x usually? It's a distance, it's a length, it's a change in the x position, whatever. What about k? It is a constant. K is usually a constant. In this case, k is what's called a spring constant. So, it's a force constant. It's a force constant associated with elastic materials. Those of you who are going into engineering will learn all kinds of constants. Some of my students, former students who've come back and talked about their engineering programs, there are a whole bunch of constants for materials that we don't talk about in here. There are constants of thermal expansion and contraction and constants of, you name it. There are surface roughness constants if you're calculating flows over something. That's all craziness that we don't do. Spring constant is really one of the only material constants that we use. If we have a soft spring, so a soft spring such as a slinky, slinkies are awesome. You'll get to play with some of them this period. It is. They have very small spring constants. They do not have big spring constants. If I hand this end of the slinky to you, and you let go of it and snap it back at me, it doesn't really hurt all that much. Getting snapped with a soft spring is not terribly painful. This one is a much firmer spring. I am not handing this to anybody to snap back at me because I know what will happen. It will hurt. So, yes, that's why I released that gently. This would have a much higher spring constant. And the spring constant is given in newtons per meter. Guess what that is? That's how many newtons of force you get whacked with based on how many meters you deform the spring. How many newtons of force that spring can store based on how far you deform the material. So something that generates, if we deform two pieces of material by 1 meter, and one of them generates 3 newtons of force when you deform it by a meter, and one of them generates 300 newtons of force when you deform it by 1 meter. You know which one I'd rather get hit with? The 3. I want to get hit with the low spring constant. Yeah. You don't want to get hit with something with a high spring constant. Garage door springs have killed people. Have literally killed people, have taken people's heads off. They have very high spring constants. It's a very stiff spring. And there are cases of, do-it-yourselfers who decide to respring their own garage doors and don't know what they're doing and literally have gotten severely injured or died. You can, where it pulls, typically. So not all garage doors have them these days. There are garages that are belt system, springless. Well, no, they still all have to have some kind of spring somewhere. Okay, some of them have an internal spring. The old ones had a big, long, heavy metal spring. So imagine a slinky made out of thick steel and then deformed under a lot of pressure. And you don't want You don't want to get in between those. We'll get there. K is something you can calculate for any elastic material, for any spring, for any bungee cord. We will be doing some calculations of K, very carefully, wearing safety equipment. So if anybody has bungee cords that they could bring in sometime next week, label, put your names on them, you know, like on the hooks with masking tape. We're going to be using those for our little lab. But K is a constant. It's a given for that material. We can look it up for some materials, but we can always calculate K. So to talk a little bit more about K and what it is, I want you to imagine this spring, and actually, let's do this. So let's say that this spring here is in its undeformed condition. Okay, it has not been stretched out. This is an expansion spring, not a compression spring. Here, it's deformed. We've pulled on this spring and we've stretched it out. And let's say that this length of the spring is 1 meter. We're just going to keep this really easy. And the deformed length is 2 meters. So the difference between those is 1 meter. If we put a Newton scale on this end of the spring, let's put a little hook here, and we had a spring scale and we're pulling on this, and to get this spring to deform by 1 meter, we had to exert 5 newtons of force. This spring would have a constant of 5 newtons per meter. Does that make sense? And it's just a characteristic of the material. So we can measure it for any spring. I could have you go through the entire closet, pull out every spring, and measure the amount of deformation and how much force it took to get that deformation. And you could calculate the spring constant for any spring. If you're an engineer and you're designing a project, if you're mechanical specifically, I can't think of an instance in which civil engineers would use springs, though they might use spring constants for materials that would not be actual springs. I don't know. I have to think about that one. If you're designing a system, you would be looking at how much tension you need on a part, like I said, especially mechanical. You would specify the spring constants for the springs you needed. And you might have a manufacturer who you say, well, look, we need springs that are 20 centimeters long that have spring constants of 135 newtons per meter. Brakes often have springs internal to them. Has anybody here done brake jobs? Okay, a couple people. Next time somebody in your house is doing a brake job, ask to just watch. A brake job is where you replace the brakes on your vehicle. And be the tool hander, whatever. Especially on drum brakes, there are springs internal that hold those pieces that hold the shoes together. And those springs would have specific spring constants. So some automotive engineer someplace, when designing that brake, said, oh, we need a spring that will exert this much tension. The force of tension in that spring has to be blah, blah, blah. Therefore, we need a spring with the following characteristics. So it's just a characteristic of the material. We're going to use it a lot, and you're going to measure it. Let's look at a practice problem. 5D! This is page 179 is the sample problem, and then the practice problems 1 through 3 are on 180, and they're assigned. We'll see how far we can get. So we have a stunt person, and a bungee jumper, a crazy person. I'll finish this as a tutorial. Watch it on your own and do the problems, and we'll talk tomorrow about our agenda going forward.